Are we back? Okay, cool. So again, this animating it, so it's really about just being able to graph this function, right? Graph this function for any change delta x, and it adjusts accordingly, right? Then later, you can just come along and just restrict the domain, right? Just like we've been doing all semester. So right now, I just want to see the graph from 0 to 1.05, or what the value of n is, right? So that the animation part is much less, much easier compared to let's actually get to graph the function. So without saying how to do it, have you been able to graph the approximate rate function? Mm-mm. So, are you wanting to graph left x? So that's the approximate rate function, the accumulation function. You're talking about over on the right? Yeah. This one? Yeah. Okay, so I'm just talking about the approximate rate function. So you're talking about this one? Graphing the approximate accumulation? What's that? So what about progress on graphing this one that I have blue, the approximate rate function?
When I graphed it, it was all connected.
Okay, and we've talked about that, right? So what's going on with that?
Basically, it's like, because it's a function, and it's basically like a rough sketch of what this curve's supposed to be.
Okay.
And so it's more kind of like, I guess, like steps, because it's like going up, how that goes.
So you have the vertical lines in between. Is that what you're showing? Is that what you're saying?
Yeah, I had vertical lines.
Okay, and we talked about that. Remember a couple weeks ago? What's happening? Why is it doing that? Why are there vertical lines?
It's connecting the endpoints.
Right, because how does GC plot a graph?
A bunch of points.
Yeah, it just does some finite number of points. It can't graph all the points because that's an infinite number, right? So it graphs a finite number of points and then just connects the dots. So we got to think. So you got to think about. You want to get rid of these. You don't want these vertical lines between the steps. So we got to think about a way to get GC to not connect the dots, right? So when we kind of explored some possibilities on that day in class. So you think about what can you do? How can you adjust? And you're not actually adjusting the function, but you're adjusting the graph of the function, because the function itself is fine. It's when you ask GC to graph that function that it puts those vertical lines in there. So when you ask GC to graph the function, what could you do to adjust it or kind of, trick it a little bit to get the image that we want to see of the function itself? So that's something to think about. So do you still have the vertical lines?
Okay, I figured it out.
Oh.
I got rid of them by accident. I don't really understand it.
Okay, you can show me later.
Okay.
You still have the vertical lines? Yeah. Okay, so we got to think about what could we do.
And then another thing I kind of didn't get is because like one of the vertical lines, it went past like one of the steps, so it didn't look like steps.
Yeah, so they went up.
Yeah,
a little bit or something.
One of them stuck out.
I think the solution to the vertical lines connecting the dots would also be the solution to that. I think once you get rid of all the vertical lines segments between the steps, then it'll take care of that weird thing too. That's just weird. I don't know what's going on there. Okay, but back to the point. Work on graphing the function. Work on graphing the function regardless of the animation. Adding the animation in is just about restricting the domain, and that's pretty fast and simple. Okay. You figured out how GC gives you summation?
I don't know.
So summation and Mac, it's Control Shift S. I don't know, maybe also in PC too. Try Control Shift S. Did you get a summation sign? Okay, so Control Shift S gives you the summation sign, and then you adjust the bottom and the starting value and the upper value. Okay, what else? So are you feeling like there's like keystroke kind of issues in GC that you're trying to do something but you don't know how to do it? Is there anything that I've forgotten to tell you about like keystrokes? Or any other issues that are coming up as you're working on this? Yeah.
I just have one question.
Yeah, sure.
The video for the delta x, the slider values were different. So do we use those, the ones that are in?
It doesn't matter because I mean, so just this is fine.
Okay.
You go from 0.3 to 0.008, but that's something that's easy to change, right?
I just want to, yeah, because in the video it had it going to like 0.0005 instead of 0.3, like the way it was.
Yeah, we want to see the big steps, right? Because we started this with 0.3. So I was showing something else when I was doing that.
Okay.
And that's, yeah, so we definitely want to start with the big steps, thinking of it as a didactic object, working through, like we did last time in class when we worked through using the delta x of 0.3.
How did you get your delta? Because I just typed it
So PC does not have that. So if you want to come up with a different, this is just a character string. This is just a string. So I use the backslash delta x backslash. So it has no idea what delta x is. Like that's not a built-in thing. So you could use.
I just called it delta, like I typed it.
Yeah, sure. You want to deltax, right? Deltax. That's fine. That works. Whatever works. So if you have a Mac, I think it's option J. Yeah, option J on a Mac gives you delta. But again, if you just write delta x, that's gonna without defining it as a unit, it's gonna just deltas is gonna be assumed to be 1, and x is gonna be assumed to be. Anyway, you have to do the backslash thing and make it a character string. Okay, someone else has a question.
What is the current slider supposed to be?
Don't worry about that. You don't have to do that. I'll show you what it is. So it's like if I showing the whole graph and then I could come along here. Well, it's off right now. You don't need it.
Okay.
It was just highlighting a particular x value after the whole graph had been generated. So it was just like a gray vertical line. I don't know where it is. So I could set it, I could set it to be here or whatever. Don't worry about current. Okay, so get the help that you need. What's today? Thursday? So it looks like you guys are ready to, with 5 days you can, and 2 days of, help from me on Monday and Tuesday. I think we can be done for Tuesday. Any questions? All right, so what is the big picture question that we're asking in this class right now, or we're working on? Yeah, and? Right. So that's kind of the theme, right? That's the theme that we're working on. If something is changing at every moment, you want to know how much you have. And so we've seen that that's consists of a progression of functions, right? A progression of functions. What's the first function in that progression that represents this process of how fast something is changing at every moment? You want to know how much you have. So what's the first function in that process? Lydia. Oh, by the way. Oh, sorry. Sorry, I was going to interrupt you, but I'll keep it on. Sorry. No, so we got a progression of functions, right? Different kinds of functions that lead us to answer this question. So in that progression of functions, what's the first one? Right, exact rate of change, right? The exact rate of change is what we started, because that represents how fast something's changing in every moment, right? That's how fast something's changing every moment. And then what's the next function in this progression? Well, listen. The approximate rate function, that's our view number 2, right? Okay, and then from there, Jason? Approximate net accumulation, very good. Okay, approximate net accumulation. And then Veronica? Exact net accumulation, right? So this is, oops, yeah. So this is our progression of functions, because you know how fast something's changing at every moment is exact rate, and you want to know how much you have is, yeah, exact accumulation. And so we could even make it 5, right? So we could say, what's the 5th one after exact net accumulation? What the hell is that?
Total accumulation?
Yeah, so exact total accumulation, right? And so that's just the difference of adding how much you had at the start, right? At wherever you're starting, 0, your A value, where your net accumulation is 0. If you have some amount from before, you just add that on, right? So you have all the accumulation from before A, and then you have the bit-by-bit accumulation after A. And so that gives, when you add that previous total amount, then you get total accumulation. Yes, ma'am?
So in this, the GC, as we make delta x smaller, the approximate should start to look like.
Exactly. So that's what we're gonna. So what is? So we really not talked much about what is the transition between approximate net accumulation and exact net accumulation. How do we get there? How do we get to exact net accumulation? Yeah, and so that's the beauty of this file is all I need to do is make delta x smaller, and then the rate function changes accordingly, and the accumulation function changes accordingly. And yours should too. Okay? And then, so is this, do we have a good approximation now? It's better. Is it good? There's a lot of daylight, right? There's a lot of daylight. And really, when we think about this, we're building toward some unknown net or exact accumulation. So how do we know when we get there? So I can get it even smaller. So here's even smaller delta x. Look at the rate function. So now the rate function is doing a pretty good job of mimicking the exact rate function. So how do we know what's small enough to call it exact, right? So we're going to just keep going smaller and smaller. So, and I think at, I don't know if I showed you this before on mine, after 0.05 maybe? Yeah, so when delta x is less than 0.05, then I turn off I have it automatically turn off the exact rate. And that's easy, you can do that. It's easy to add a statement in there. So now when it's delta x is small enough, it just shows the approximate rate, which is pretty close. So how do we know what's close enough, right? So I can go to all the way to 0.008 here. Here's 0.008. Exact or approximate rate of change?
I think it still would be an approximate.
Right.
It's really close to exact because your delta x is like getting really close to 0.
Right. And look at the graph. I mean, so yes, yeah, well said. Technically, it's still approximate, but the delta x is so small that it's a really, really, really good approximation. So when do we know when to stop? When can we call it a day? We can't make delta x 0. What happens if we make delta x 0? Can we do that? Can we make delta x 0?
I was thinking yes, but I don't know.
Well, because when you are solving for the net accumulation, you divide by delta x.
Mhm.
So you can't really make it 0. And then you're dividing by 0. So
Yeah, and how is it that we're generating accumulation? Right? What's the key, the heart of all this to generate accumulation from rate?
a bunch of small rates, constant rates.
Right? And what's the core math principle behind this getting accumulation from rate? Good. And how can we get little dy if that's 0? We can't do it, right? Yeah, so this is the idea of limit, right? This is the idea of limit. That at some point it's small enough that we can call it a day. But you can't make it 0. But that's what a limit is. A limit is what would happen if it did get to 0. But we can't make it 0, or else then all our changes are 0. You see? That's awesome. That's great. I love that. I love that you're going there. Yeah, but this is the whole idea of a limit. What is a limit? A limit is this place that we would arrive, but we can't get there without things falling apart. But if we were kind of able to get there, what would it be? So does that make sense? Yeah, that's what limit is. So limit is like, so small that it's essentially a delta x of 0. But it can't really, theoretically can't be that. So what happens is it's like, look over on the right at the approx. So is this approximate or exact accumulation? The pink one. It's approximate. Really, really good. So it's the kind of idea that, so here's 0.07. Now if I change it and make it smaller, so I'll pause the graph. Does this change? Does the approximate accumulation change when I make delta x smaller? Watch it, ready? Did it change? You saw it change? Okay, so maybe we need to go smaller then. All right, now watch now, from here to here. Did it change? All right, so now this is why I did the 0.005, okay? All right, ready? I'm going to change it again. Tell me if it changes. Did it change? Well, it blinked. It redrew it, but did it draw something different? So here I am at 0.008, and if I make delta x smaller, I'm essentially getting the same thing. So maybe 0.008 is something like small enough that these approximations aren't going to change anymore. The approximations themselves are so close together, or they're essentially the same, that then we can say that's the exact accumulation. And so then that's this. So how close is small enough? It's whatever delta x, such that if you make delta x smaller, you wouldn't get something different. It's just the same thing over and over again. That's small enough. And so then when we reach that exact net accumulation with delta x really, really small, oh, these work. I need to be able to write. Yes. Yes. Okay. But now my cursor's not there. Ah, come on. Oh. The light is on, but doesn't work. Why not? There we go. All right, so then our exact net accumulation, so approximate is just A. Exact net accumulation would be A sub W, just like the exact rate was RW. Approximate rate was just R. Approximate accumulation is just A, and then exact accumulation is AW. So when delta x is small enough, we have a different way of writing this bad boy, right? This complicated equation. It's a lot simpler and cleaner and streamlined. What is it? Anyone know? So how do we write this for a very small, so if delta x is small enough, right? So that the approximations aren't getting any really better anymore. How do we rewrite this in a streamlined way? Let's just got it. Jason, do you know?
Because I agree with Melissa.
Huh?
Because the integral
Uh-huh.
would mean that your delta x would be infinitesimally small.
Right. An integral of what? So what was the gist of this, right? This all this complicated stuff, we said, so important to never forget what it all boils down to. All this complicated stuff in here boiled down to what?
Oh, isn't that like it's the accumulation of all your little delta x's?
Right. And how do we get accumulation, right? Summing up what? What? And just in a
Oh, summing up the accumulation of all those moments?
right. And how do we do that mathematically? What is it?
Oh, multiply a rate by a change in x.
Good. That's all that boils down to. It's just a bunch of m times changes in x, right? A bunch of m times the change in x, adding all them up, right? So it's the same thing with integral. It's going to be the integral of what? What is m? Now it's kind of like instead of over intervals, it's kind of like every single rate for every single value of x. What is that? Every single rate for every single value of x. RW, right? You know how fast something is changing at every moment. RW. Rate, what? dx. This is multiplication. The dx matters. It's the change in x, right? So now it's kind of like when delta x is small enough, it's kind of like every single rate times itty bitty teeny little changes. And then the integral means? What does it look like, Anna?
Oh, integral's the what makes it accumulation.
Right. What is it? What letter does that kind of look like?
S.
S. It is. It's a German S. It's a German S. Standing for? Sum, right? Sum. Just like we summed up all the m change in x's in the approximate rate function, we're still summing up a bunch of rate times change in x. Sum of rate times change in x. Starting from wherever we're going to start our accumulation up to x. Now this isn't right because we actually have to. What's wrong with this now?
Oh, don't you need to replace your x with t?
Yep.
Or will
And
the t, will the x in the front and the
yeah, so we need here, we need t's there, or something else, some other symbol besides x. Why? Why did I need to, why can't I put x and x here and then integral from a to x?
Because we already have it, we would think that we were saying the t in the function is the same as like the value that we're going to,
Uh-huh.
instead of starting from a specific value to another.
Okay, yep.
essentially t is in between that value of a to x.
Right, so that what happens? Right, we need we need t to vary from a to x, so that what happens? So imagine if there were x's there and we did a w of 3. And a w of 3 would be integral from a to 3 of what? R w of 3. If it were an x there, right? If x. And what does that mean? Is that what we want?
No,
What happens?
what do you do the rate of where we're at 3
Uh-huh.
multiplied by these infinitesimal, like changes in x?
Which ones? Which ones would the rate at 3 get multiplied? In what intervals?
By all of these?
Right. Do you see it? What would happen here is that as you started accumulating from A, what rate would you be accumulating at? Close to A. Yeah, close to A. What rate would you be accumulating at, according to this? What's that? The rate of 3. And then in the middle, what would you be accumulating at? The rate of 3. And toward the end. So you would, from A to 3, you'd be accumulating at what? At a constant rate the whole time of that final rate. And why is that wrong? Yeah, we need to accumulate at all the different rates starting at A to 3. So we don't want that because that'll just accumulate at the constant rate the whole way, the ending rate. So that's why So that's why we need t's here, right? So t represents every value from a to x, so we get every rate from a to x, right? We get every rate from a to x. Okay, and so then on GC, integral symbol is Control Shift I. Try that on GC. Make sure you get that Control Shift I.
Yeah.
Does it work? Okay. So. So this is kind of the mathematical kind of conclusion to our question. You know how fast we're. We'll talk about it in a second. Any questions on this? All right, so I've got a slide to kind of practice the ideas here. Can I erase and go on? So just generically, we were dealing with the W, right? Generically, a sub f of x. Think of this, we're going to think of this as this, right? It's the same thing. But under what condition? Delta x is really small. So they're the same when delta x is small enough so that values of a, the approximate, are indistinguishable from exact. No, this is the wrong slide. What am I doing? This is not the right slide. This is the right slide. Okay, so yeah, so delta x is so small, they're the same. The accumulation in the current interval is just like all the other accumulation in the previous intervals because that delta x is so small, right? So it's not like you have a smaller change in x. Well, delta x is already so small anyway, so that last current interval is just kind of like the last completed interval. Make sense? So we can just think of just including that with the sum. It's like that current interval thing, and now it's just like the last completed interval because they're all small, right? They're all super small. Okay, so I just want you to practice here. So for each one of these 1 through 6, you're finding how that statement, that phrase, is expressed in both. So we know how fast something is changing. How is that expressed in the first one? How is that expressed in the second? We want to know how much we have. How is that expressed in a sub f? How is that expressed in the a function? So you talk to your tables, go through each one just to practicing that. How are these the same? When you see integral, you think this because it really comes from this. Question?
Yeah, I'm actually still kind of confused on when you took out the current interval and the second one. If the intervals weren't, like the delta x weren't super small,
Yeah.
is that when you use the current?
Yeah.
Or, okay.
Yeah, we need the current because then it's difference, right? If delta x is not small,
Yeah.
then we need that little more accumulation in the current interval, or else we'll get a really well, we won't get what will it look like? We won't get the piecewise function, right? It'll just be like, you'll basically, anyway, I'll get into it. Yes, when delta x is not small, we need that little bit of accumulation, or else this is very inaccurate. So in the current interval, it gives us that, like we did in that quiz last time. But then when delta x gets small, there's really no distinction between the current interval and the last completed interval. They're kind of the same. So, does that help? All right, so talk through these. How are they the same? Go. How is each one of those 1 through 6 the same? Or, no, sorry. How is each one of those 1 through 6 seen in each of those, right? Seen in each of those. This is the most important one, and it's the one students always miss. So I'm just warning you. It's the most important one. It's the one students always have trouble with. Summing up many bits of change. Summing up many bits of change. Okay, we ready? Think you got them?
More or less.
Yeah.
Okay, so we know how fast something is changing. Where do you see that in the first one?
The rate.
He wants the rate function, agree?
Yes.
Yep, the rate function. Exact rate in the integral, approximate rate, and our approximate accumulation. We want to know how much of it we have. What's that?
Integral and summation.
How much do we have is just the integral symbol?
Oh, no.
How much do we have?
I was thinking R sub f of t dt, like the
We want to know how much we have at every moment. We want to know how much we have at every moment. That's what I'm asking. She wants the left sides of the equations.
Yeah.
Jason's changed his mind. What do you think?
Because
Okay?
hadn't thought about that.
Yeah? Yes. This is what we're after, right? We want to know how much we have at every moment. Okay? Which is found by summing up many. What's that? Which is found by summing up many. Where do we see that in both? Where do we see that in the top equation? Summing up many. Or summing up more than one. The integral from a to x. And then the bottom one? Sigma, right? This is number 3. It's found by summing up many. Okay, here's crunch time. See if you guys can do better than previous classes. Bits of change. Bits of change. We're summing up bits of change, right? Where do you see that in the top one, and where do you see that in the bottom?
I would say
Okay, I said, because it says actually not dy, I said the R sub f of t dt.
She wants r sub f of t dt. That's a bit of change.
MDX.
What's that?
Since dy equals MDX.
Yes. Right. Right. Yes. Remember that, like the last couple of weeks, it's like we're just summing up m times change in x plus m times change in x plus m times change in x. That's what this does, right? But in a nutshell, that's what it does. Each one of those is a little bit of change. And we're accumulating, right? We're accumulating. Okay. The starting value of x is a to the current value of x. X, right? So x there or x here. Okay, so whenever you see integral from now on, what goes through your mind? This. Too far. This. So whenever you see integral, it's this, right? right? It's a summing up of all these bits of change. Each bit of change is calculated by what? Each bit of change is calculated by MDX. Summing up a bunch of those, and that's how we build accumulation. So each little bit of accumulation is calculated by the rate of change. So this is why. So in this program, this you're doing the bachelor's of math with the teaching certificate. You're doing that. Have you noticed that there's been this in these classes? There's been this huge emphasis on constant rate of change. Why? Why do we talk about constant rate of change so much? This is the answer right here. Why are we talking about constant rate of change so much?
It's like,
Well, be a little more specific.
I feel like it's used a lot in a lot of different lessons, regardless of like the level of math.
Okay, well, why am I asking this question right now, this moment? There's a reason I'm asking the question right now. Why is constant rate of change so important?
Because since we know how fast something's going, we want to know how much it is.
Okay. Right? Yeah. And what is the key to that? So now we found the key. We found the key to that. The key to we can know how much we have if we know how fast it's changing. That's the key.
Make the moments really small.
Okay. And mathematically, how do we represent that? Yeah. Integral. What is the core principle of integral? Well, yeah, okay. But what's the core principle behind integral, behind being able to accumulate?
People add up all of your
Constant rate of change. Yes. Constant rate of change is the core idea in order to get us accumulation. So the reason that we're so big on constant rate of change, understanding it, is because it's the foundation of integral, right? That's what it's all based on. That we're accumulating at constant rates, right? We're accumulating at constant rates times changes in x. Okay, so let's. I got to practice. Just practicing using. Oh, so when I almost interrupted Lydia before, is what I was going to tell you is, so we're going to have another assessment Tuesday, and that assessment's kind of a double assessment. It's almost a test, and it's on this whole thing. It's okay. It's math class. We need tests. Okay.
Wait, so it's almost a test, but it's not?
Well, it's like twice as long as the assessments, or maybe two to three times as long as the assessments you've taken so far. So it's like a test, but it's another assessment. It's just like a double assessment. Okay. So and it's all about rate to accumulation, right? So this whole thing we've been talking about, including integral. Everything we've worked on in the last 3 to 4 weeks, where we've worked on, you know how fast something is changing, you want to know how much of it you have, and we've built from the ground up, right? We've built the mathematics from the ground up until we've kind of like arrived now. We arrived at the final conclusion. Integral net accumulation function, which gives us exact net accumulation. So the assessment Tuesday will cover all the aspects of how we built this integral up from the ground up over the last 3 to 4 weeks. Okay? So there's a little practice here, a little integral practice we can work on here. So I'll give you guys 7-ish minutes. Work through this, talk through this. you need to think to yourself, that's fine, but I always encourage collaboration. Right? I always encourage sharing ideas. Okay? So maybe a question 0 would be, make sense of this rate of change graph as a whole. In the situation. Why would it make sense that this could be the rate of change of water emptying or water coming into the tub? Think you guys got it?
Yeah, we're stuck on
I guess you're stuck on E because you were unclear on D. What is the function a sub v? What is it? What, describe it to me. What does it do? What does that mean? Accumulated changes in volume.
So at every moment, you add up those moments of accumulation.
Okay. But what does that value give? So if you did a sub v of 3.6, what would that value mean? A sub v of 3.6. What would it mean?
That gives us accumulation when the water, when the water has been running for 3.5 minutes.
Okay, so that's a little vague. Can you explain it without using the term accumulation? So a sub v of 3.6 would be what? What would that, just describe it like if you're describing it to a child?
How much water you have at 3.6?
How much water is in the tub at 3.6? Is that what that is? Lydia, you agree? How much water is in the tub at 3.6 minutes? Gives the accumulated changes in volume. Accumulated changes in volume since t equals 0. Is that what the problem states?
Yes.
Okay. You're saying it's volume of water in the tub. You said this was how much volume is in the tub. And it's described as accumulated changes in volume since t equals 0. Are those the same?
No, because volume in the tub would mean that, like, you'd already know how much was already in the tub.
Okay.
And so you just add
What is this? So describe to me what this is on the left, because that's what D is about.
how much, or
Without using the word accumulated or accumulation, what does, if you're explaining to a child, what does that mean? What it's saying?
how much water you've gained at 3.6 minutes
Since when?
since the faucet started running, which is it.
Veronica, what do you think?
Well, Tony's problem, I guess it's kind of confused because it starts with 2.5.
Mm-hmm.
So it would be from 2.5. No, wait. mean, it made sense what Jason was saying. I was just having confusion with why 2.5 is there.
To confuse you. That's why it's there. To make sure you know exactly what's going on. It's there to confuse you. So what does accumulated changes in volume since t equals 0 mean? Lydia. So use the same words that you've heard someone else say. That's fine. That's okay. What's that? Is it the volume of water in the tub? Is this the volume of water in the tub? So back to this question. Is this the volume of water in the tub? Veronica, what do you think? Is it the volume of water in the tub? The accumulated changes in volume since t equals 0.
I'm gonna say no, because I feel like saying accumulated changes, that's sort of fine. It's gonna be that the rates times the change in the time.
That's what?
The rates at each moment.
Okay.
Times the rate at the change in time.
So where's the first accumulated change? So where's the first one of these? Where's the first accumulated change?
Let's say if we zero the faucet's 10 mils, that's when water starts going into the tub.
Right. So the first accumulated change maybe is from t equals 0 to t equals 0.01 minutes. That's kind of like the first one of these. So if AV of 3.6 is 5.9 gallons, what is 5.9 gallons? How would you describe that? Simply.
Is it how much water you've gotten at 3.6, but you don't know how much is actually in the tub?
How much you've gotten at 3.6? How much you've... How about added by the faucet or put in by the faucet, right? So this is the water that's come out of the faucet since t equals 0. Is that the volume of water in the tub?
No.
Why not?
Because
Because
that's the line there.
it hasn't told us how much is in the tub yet, so we're just going off of like.
Is it a net accumulation? Like, it's not total. Just like Jason was saying, you don't know exactly how much is already in there to begin with. It's just
Right.
how much the faucets release.
Okay. So then how would you write the expression, Veronica, for D? A sub V of that. Are we doing T here? T, yeah, T. A sub V of T is what?
You said the integral?
Integral?
A to X.
A to X?
R d of T.
Is this right?
I did 2.5 plus, but that's why I
Is it 2.5 plus?
Well, yeah, you add
We
plus.
actually started with that.
You're going to add the 2.5. What would that give you if you add the 2.5?
Total.
The volume of water in the tub. Is this the volume of water in the tub?
Now,
No, it's not the volume of the water. What is it?
the
Accumulated changes. What does that mean? Accumulated changes since time equals 0. What does it mean to a child?
How much water has been since we started. So how much water has come out of the faucet?
Right. How much water we put into the tub since time started. Is that what this is?
No, that's total.
No. So what? How are you going to write this function?
Without the 2.5?
Yes. This is net accumulation, right? This is how much change since time equals 0. But there's still a big problem with this.
You say 0.
What's that?
Oh, it's
Okay, you can put 0, that's fine, but there's still a big problem with this.
Is it because we we started with 2.5 gallons.
No, it's about variables, right? What's the independent variable?
Oh, independent variables
T.
So we can have
You don't need for X.
So what do we need to do?
Is it RV of X?
AV of t means we're integrating from 0 to t.
Yeah.
And we need something different here.
Can we say L?
What's that?
she said L. Why not?
Yeah, let's do U. And then what's the volume function, V of t? What's V of t? You can go. Go ahead. What's V of t?
It'll be the volume of the
What's that? Now, how would you write the function for V of t?
So you're saying total would it be a 2.5 times?
This is the total volume in the tub. So what would V of t be? We want the total volume of water in the tub. What was this again? Accumulated changes. How much water has been added since time equals 0, right? So how do we get the total volume in?
Sorry, is it 0 plus all that?
What's that?
0 plus?
0 plus?
Starting it from a, like,
Total volume of water in the tub? We have the 2.5 gallons from before, plus this. Plus now the accumulated changes from since t equals 0. Oh. You said it for a sub v.
well, I had said it again, but then I was wrong. So. I thought it was